Welcome, students. In this video, we are going to continue to study the techniques of differentiation, and today's topic is the product and quotient rules. We are going to use, as usual, these rules later on when solving practice sheets. Okay, let's start. We are going to start by proving the product rule. So if we have two functions f and g that are differentiable at x, then their product is also going to be differentiable, and we can find the derivative of the product of these two functions as first function multiplied by derivative of the second plus second function multiplied by the derivative of the first function. Okay, let's show why this is true by looking at the limit definition of the derivative. So derivative of product of f and g can be expressed as limit when h is approaching to 0 of our product of functions at point x plus h minus their product at point x divided by h. Okay, now we are going to do the following trick in an attempt to split up the stuff that we have in our numerator. We will group them up in the following nice way. We are going to artificially add and subtract term f of x plus h multiplied by g of x. Then we are going to group up first term that we have here with the minus fx plus h multiplied by gx, and we'll factor out f x plus h. So we'll be left with g at x plus h minus gx. Next, then we are left with plus fx plus h multiplied by gx and our second term here. Here we can factor out g of x, and we'll be left with fx plus h minus f at x. All right, everything divided by h. Now let's pay closer attention to the following fractions. This one and second is the following fraction in blue. Okay, so what can we see here is that if we look at the ratio of the difference that we have in these square brackets over h, when limit is approaching to h0, this is exactly a limit definition of derivative of g multiplied by f at point x plus h. When h is approaching to 0, this is simply f at point x. And second fraction in blue here, square brackets divided by h is limit definition of derivative of f multiplied by g of x. So we are finally going to be left with f when h is approaching to 0, this is simply x multiplied by derivative of g plus this is g. So basically here we can factor out this out of limit sign since it's invariant of h multiplied by derivative of f, which was required to prove. So basically, let's assume that you would want to find derivative of product x squared multiplied by e to the power of x. Then let's define your x squared as function of f of x. And let's define our e of x as function g of x. Then to find derivative of the product, we have to find the following sum: x squared multiplied by derivative of g of x, which is e of x, plus e of x multiplied by derivative of f of x, which is going to give us 2x. So the answer is then, if we factor out e to the power of x, is 2x plus x squared. Right, this is pretty straightforward rule. We'll show how to solve some other problems using this rule later on in our next practice sheet. All right, next rule is a quotient rule. If f and g are both differentiable at x, and if g of x is non-zero, then f over g is differentiable at x. We know this from differentiability that we studied a couple of lectures ago. Now we can find the derivative of their ratio using the following formula: g term in numerator multiplied by derivative of term in denominator multiplied by derivative of numerator minus numerator multiplied by derivative of denominator divided by denominator squared. So let's show why this is true. Again, starting by looking at limit definition of derivative of the ratio. This is limit when h is approaching to 0. So the value of the ratio at x plus h minus f of x over g of x, everything divided by h. Let's bring them to common denominator. We'll end up with limit when h is approaching to 0 of f of x plus h multiplied by g of x minus f of x, g of x plus h divided over by h multiplied by g of x plus h multiplied by g of x. Now let's apply the same trick that we used for the first proof. Let's artificially add and subtract the following term: f of x, g of x. Then we will group the following terms in numerator. We'll group first term with minus f of x, g of x, and we'll factor out g of x. Here we'll end up with limit when h is approaching to 0, g of x in brackets f of x plus h minus f of x. Second, we are grouping up this term with plus f of x, g of x, and factoring out minus f of x, we'll end up with g of x plus h minus g of x. In denominator, we'll be left with h, g of x plus h multiplied by g of x. Now let's split everything up in the following manner. We'll have limit when h is approaching to 0 of 1 over h, g of x plus h multiplied by g of x multiplied by, let's actually group this with the following term. So in numerator, we'll have g of x multiplied by f of x plus h minus f of x, and let's squeeze in that h inside of the following brackets. Minus, I will explain in a second why we are allowed to do that. Let's deal with the second term for now. Limit when h is approaching to 0. Let's group them in the following manner. So we'll have f of x over g of x plus h multiplied by g of x multiplied by the following ratio, g of x plus h minus g of x over h. Now look, recall that f and g's are differentiable functions, meaning that they are continuous. So this term is invariant of h, so we can factor it out of limit notation. Since g is differentiable at x, it is continuous at x, meaning that limit of that thing exists. Actually, those two will cancel out. Then this term here is simply a limit definition of derivative of f, and we know that f is differentiable, meaning that this limit also exists. So we can split them up in the following manner. Next, second term we have here, f is differentiable. In fact, this is invariant of h. We don't care. G is differentiable, meaning that it is continuous. So limit of that thing exists. And G is differentiable. So this is limit definition derivative of G, meaning that the limit of this exists. So we are allowed to split those limits in the following way. Now let's see what we'll end up with. A limit of 1 over g of x plus h when h is approaching to 0 is simply 1 over g. This is g prime minus, this is f over g, and that's also g. So this is f over g squared multiplied by, this is g prime. Bringing that to common denominator, we'll end up with g multiplied by g prime minus f multiplied by g prime divided by g squared. Okay, guys, I think I missed something here. Let's see. Oh, this is not g prime, this is f prime, right? Yes, this is f prime. So that's f prime. What was required to prove? Derivative of term in just the term in numerator multiplied by derivative of term in denominator multiplied by derivative of term in numerator minus term in numerator multiplied by derivative of denominator divided by denominator squared.